So it came to my attention from the other day that it didn't sound like all of you were hearing the resonance. I kind of wanted you to hear it. We're doing the speed of sound thing, just so you guys could see exactly what's going on. Make sure you actually recognize what we were looking for. So this is our 256 tuning fork here. So we strike that, we get to vibrate at its natural frequency again to a force vibration. And then we're going to extend the length of the tube. And at that point right there, hopefully you could hear the difference in the sound that it made when it went from 2 as it found its resonance point, when that frequency hit that first harmonic. Here the 512 will be about half that height. So there again inside, what we're doing is getting the exact right wavelength. We're getting the max amount of constructive interference at the opening to get that first harmonic to be at its loudest. So again, here's the 1024, and hear that one, basically right there at the beginning. It's its loudest point, but then like we did in the lab, let me hit it again so we make sure it's vibrating. You can, that third harmonic shows up there near the very peak. So hopefully that helps you guys hear that a little bit better. We were trying to get at the other day. I know you took the data down and kind of went off what I told you, but hopefully there you could hear audio-wise the difference in the sound as we hit the right column lengths to generate that maximal frequency for that first harmonic, and then even the third harmonic for the 1024. So hopefully that helps you guys understand like what's going on a little bit. Again, on Monday, we'll go over any questions that you guys have before we take the quiz. We'll kind of work through the worksheets and stuff like that. So just to take you through the video a little bit more and talk about the lab that we're working on. Okay, again, here's the water level, here's the tube, here's the tuning fork up on top, and again, it's vibrating back and forth, which is going to cause compressions in the air around it, and then rarefactions when it comes back. So we can take those compression waves and kind of draw them as transverse waves the other way around. So we could say maybe we're at we'll call this a peak crest at the start, and as it travels down, when we hit the right wavelength, we're going to hit the bottom, and when it does that, it's going to reflect backwards. Remember, it's continuously sending waves down, so this is the point where that interaction is happening perfectly. If it's not the right length of tube, you're not going to end up with this perfect interaction where that reflection point will be there. If we're shorter than that, say the thing was up here, we'd hit here, reflect back, and things wouldn't be aligned. But if we were hit, say, up here instead, obviously we'd hit here, reflect back, but we'd still be traveling that way. It wouldn't be quite right. So by going to the exact right length, we hit that node right here. We have our anti-node here. And because we have our anti-node at the opening, that's going to give us the greatest amplitude and loudest sound. So that's why we're hearing that resonance point when we get the exact right length of tube. If you look at this too, if we're going from a crest to a midpoint, okay, that means that to complete an entire wave, remember we have to go crest to trough, back up to crest again, right? So in this one, we've gone from crest to midpoint. If we bounce back up, okay, that's when we would have hit the trough again. So that means the entire length that the sound travels up and back, down and back up again is going to be a half wavelength. But that means that the height of the tube is only going to be from there to there, which is a quarter wavelength. So hopefully that's making sense as to why that's happening with the resonance in the speed of sound lab.